Alright, so please sit down. Take a seat or take a stand. So we have everyone. Please arrange yourselves and we can start the discussion. Thank you very much.
So, you're going to get started. Can you all please get finished?
Hello everyone, we're going to get started now. First, leaving from Google actually everyone and we have audio
Good morning, good afternoon, good evening. Hello everyone. Please settle down a little. To talk to your friends. But we don't have much time for that. We have a distinguished panel here. And students would like to share their opinion on the issue. Okay, so we're just going to get started. I think you can settle down so that we can hear the conversation. I'm Anthony. I'm from Oakland, University of Washington. And I would like to welcome you all to this incredible panel. The topic for tonight is on scalability and also on industry and academia. So, the audio is really good. Hello. Take a seat, sit on the floor, sit at the table, but settle down a little so we can hear our distinguished panel on a really interesting topic. There's lots of room outside if you just want to mingle with your friends, but if you'd like to hear what these scientists have to say about our future, then that's what we'd like to do here. I'm Hank Levy, I'm from Google at the University of Washington. I'm very happy to be here tonight. Google has sponsored this panel, and we'd like to welcome you and looking forward to hearing the topic. The topic tonight is systems at scale, research at scale for both universities and academia. And this is a really important topic. In fact, I came to Google to spend time after 15 years as chair of the University of Washington because I didn't think it would be possible to really understand the scale of computer systems today without going to industry. So this is kind of where we are. It's maybe a little extreme, but I actually think that cloud computing, warehouse scale computing, is one of the most complex artifacts ever created by humans. We can debate that later if you like, but this is an extremely complex thing, and it's amazing how well it works. And we want to make sure that the future is invented by people both in industry and academia as well. I just want to mention finally that Google is very interested in computer architecture. Also, David Kohler and I have started a new research group in computer systems called Systems Research at Google. And we and many groups at Google are interested in hiring in this area. If you're interested in looking at opportunities, talk to me or Partha or Samira or many of the other people here from Google. Thank you very much.
Today we have a star-studded panel who have been pushing the boundary of computer architecture in both academia and industry. They all have made fundamental contributions in our community and they have a long list of awards. So I will skip those and I will just briefly introduce all of them because literally they do not need any introduction. I'm guessing everyone knows our panelists. First, we have Babu Falsafi, who leads the first lab at EPFL. He founded the EcoCloud Research Center, and he was the first few people who contributed to cloud architecture. Sean Lee leads the Boston SysML Research Group at Meta. In his previous life, he was a professor at Georgia Tech. He has been innovating in ML hardware and systems and leading the path for scalable hardware in the cloud. Bobby Monday recently joined Meta after spending 2 decades at Microsoft, Cavium, Intel, and AMD. And currently, she has a mission to architect a sustainable planet. Next, Margaret Martinosi. She's currently serving as the director of SINS at NSF, also being a professor at Princeton. She has been a pioneer in introducing formal verification and practice in our architecture. Partha Ranganathan is a VP at Google. He spends his time designing Google's next generation systems. Anything related to systems and hardware that comes out of Google, there is something Partha has contributed. So let's begin. The format is each panelist will actually talk about their viewpoint in the form of a position statement. Then we will have some follow-up questions based on the statements and we will open up question and answer from the audience. So just a small request, we are live streaming this panel and apparently the noise from the audience is interfering with the live stream. It would be great if we can be quiet for just a quick moment so that we can make the hybrid conference success. So this is the first time we are in person, but at the same time we are attempting for a hybrid conference. So let's please make sure that the audience who cannot be in person can at least enjoy what the conference. So first, Partha, do you want to talk about?
Okay. Hello everyone. It's a pleasure to see so many people in person. Hello everyone. It's a pleasure to see everyone here in person. So, and hello to the people watching this online as well. My name is Partha. I'm a fellow at Google. So today's prompt was about talking about research at scale. I was initially going to call this 5 jokes and a quote, but I decided I would keep it a little bit more straightforward. But I want to give a shout out to Father's Day today. So can we have a round of applause for all the fathers here? Well, I woke up at 4 a.m. today morning and my dad lives with us. And so I woke him up and wished him a happy Father's Day. And so, so I figured I would introduce a few bad dad jokes throughout the talk. So I'm not going to try to present the jokes, but hopefully you'll get a kick out of this. Can I have the next slide, please? So can you skip the animation as well? Oh, back. Okay, so so what does research at scale mean? So I'm incredibly fortunate to work at Google, where when we talk about scale, we are talking about the planet scale computing that powers the world. We have 8 applications or 9 applications, each of which has like 1 billion users, And what is very interesting is when you are writing an application, when you're designing a system that serves 1 billion or 2 billion users, things get very interesting very fast. And we have an expression at Google where we talk about how everything changes when you scale 10x. And so I'm going to talk about 5 vignettes of what could be interesting. So the first thing I want to talk about is data at scale. So we have again this joke that I like to use, what you call 20 petabytes of free disk space, and you can read the punchline there. But when you think about big data, and you think about the multiple petabytes, exabytes of data that we have, the trade-offs between the memory hierarchy in terms of storage, disk, flash, memory, that is by far one of the biggest interesting challenges we face. Also, beyond storage, if you look at data-centric computing, if you look at the computing associated with analytics, with serving data, storing data, curating data, processing data, I think it's one of the biggest challenges there. So the first vignette I want to kind of offer to everyone to think about is how do we think about data at scale and what are the big challenges there? The second vignette I want to talk about is around core design at scale. So how many people here have heard of the TPUs, the VCUs? Okay, how many people here have heard about Untitled? Okay, a few people. So I think we all know that we are in the new era of Moore's law, the one which is defined by custom computing. But one of the biggest challenges is when you think about co-design, scale really adds a new complexion to that. So if you think about the video coding accelerator we designed, the trade-offs that you make when you design an accelerator as an ASIC versus designing an accelerator as a system, which is going to be deployed in 1 million servers, are completely different. And the second challenge with accelerators really is around capabilities. So when you start thinking about the TPU, the first machine learning accelerator we didn't design it because it was an efficient hardware. We designed it because it enabled us to have new capabilities that was otherwise not possible. For example, with machine learning, we were able to kind of take training that was order based and bring it down to a few hours. With video coding accelerators, we were able to take video that was otherwise not possible, 4K video and so on and so forth. Similarly, software-defined hardware is a pretty important thing as well. Okay, so the third vignette I wanted to talk about is trust and security. And once again, if you think about the challenges we face at scale, when you have like millions of servers, things that otherwise are pretty egregious can be pretty significant as well. And one of the biggest things that we are very worried about is this notion of silent data collection, where when you have systems at scale, you start seeing things where compute don't compute anymore. And so that's the third vignette that I want to offer as an important challenge that you look at scale. And then the fourth one, I think other panelists are also going to talk about it at depth, so I'm not going to go into too much details. But if you think about sustainability, and if you think about the footprint of all the computing that we have, that's again a fairly significant challenge. And most companies have a 24/7 carbon-free pledge that we're kind of looking at, and that has some very significant challenges that we need to face as well. And then finally, Hank mentioned this briefly. If you think about one of the biggest changes in our industry as a whole, the notion that we are transforming our businesses to be more digital, the notion that we are modernizing our infrastructure. And if you think about where we are in cloud, we are really in the very early stages, right? We had infrastructure as cloud, and we are now starting to think about the transformation of cloud as well. And we are still in the very early stages, and so I think there's a whole bunch of significant opportunities there as well. So that's what I wanted to leave you with. I think research is fascinating in itself, it's really exciting, but when you start putting in scale, I think the opportunities ahead are fairly significant. So thank you there.
Hello, everyone. I'm trying to watch my notes and my timer at the same time. I'm Margaret Lucy, and I lead the Directorate for Computer and Information Science and Engineering, the SCIENCE Directorate at the U.S. National Science Foundation. We have a budget of $1 billion. We fund around 80% of the academic CS research in this country. And so there's a good chance that if you're at a U.S. academic institution, we pay your salary. An inspiring picture for me about science at scale and about computing at scale. So this is the picture that was released last month of a black hole imaged within our own galaxy. Imaging a black hole is a pretty mind-blowing thing that made front page news 3 years ago when they first imaged a black hole. This one is local to the Milky Way galaxy. So why is it in a computing talk? A couple reasons. First of all, tens of millions of CPU hours funded by NSF SCIENCE contributed to the creation of this image, and through resources and programs that you can use too. But second of all, there was computational photography research that led to this image as well. And in fact, one of our early career awards in the computing directorate this past year went to one of the 4 scientists who was part of this press release. She, as an NSF, you have to write annual reports and final reports, but what our impacts is that she imaged a black hole this year. Not bad. Next slide, please. Great. So that was my attention getter. It didn't really quiet the crowd down, but anyway. What I wanted to talk about was research at scale and how to do it. Key thing is pairing research topics with research resources. So data centers and commercial cloud are a key research resource. Totally with you there. Also, data at scale and available to all researchers is important. And it's important because we're seeing a brain drain from academia out to industry people following the data. We love to make the data available and federate it across sources so that people can stay where they are and do research at scale. Semiconductor fab access is another form of research at scale. Most NSF-funded researchers have not taken their ideas to fab. We'd like to see more of that. We'd like to fund more of that. And quantum computing is an example of cloud-connected public at-scale prototypes as well. So NSF has a range of efforts that contribute to this. Hey, I pay your salaries. You remember that part of my time? Great. NSF has a range of efforts that contribute to these goals, and we don't see this community coming in at the level that they ought to make use of those efforts. If you want to use the story from paper scale engine, we have one. You can program for it. So go after these efforts and make use of them. Last line here, relatively small font, $6 to $100 million. We have infrastructure funding available to fund research at scale, to fund infrastructure at scale. We don't see enough of you coming in there either. Unenforced scale, topical scale. Application focus across things that are bigger than just CIGAR, bigger than just TCCA. Where are you coming in to address climate modeling at scale across many communities? How will ISCA community help on things like that? Geographic scale across national and global scale wireless systems. And people scale. How do we organize as a community so that instead of 5 people on an ISCA paper, we have 500 people? What could we do if we set out as a community to solve one problem together over the next 10 years? Thank you for your attention.
Hey everyone, I'm pretty big voice, so I'm gonna shout it out. So I'm gonna talk about research at scale and looking at sustainability. Next slide, all right. Which button am I pressing? There you go. All right, 50 years ago. Most of you are not alive in this room, but 50 years ago, we had one computer for each business, which meant it served hundreds to thousands of people. Move forward now, we have multiple computing systems or connected devices per person. Average US household has 13 devices connected per person. Average US person has 3 devices. All right, and then all of this is supported by the developments of the last 50 years, from the internet to the cloud computing to most recently AI. So all of these devices, from the cell phone in your hand to the systems in your data center, have a carbon impact or sustainability impact. From what's called cradle to grave, to mine the materials, manufacture the device, use the device, and eventual disposal of the device. We generate 50 million metric tons of e-waste every single year. So this at-scale computing has a negative cost associated with it. And you might say, all right, we can do as computer engineers what we've always done. We can make things more efficient. Guess what? We are orders of magnitude more efficient than we were 50 years ago, and we are orders of magnitude more equipment than we had 50 years ago. And this is known in economics as Jevons paradox. Fundamentally, you make things more efficient, which results in more use. Okay, so that is not the way to solve this particular problem. And you can see this now if you look at Facebook, Facebook data centers and look at AI. So over the course of 18 months, we have a 3x increase in the amount of AI infrastructure capabilities. And this scaling is continuing. So we have 8 billion people in this world. 5 billion of us are connected to the internet. 3 billion of us have to still come onto the internet so they can benefit from the internet economies that we have and the business opportunities that it provides. So how do we scale another 40% and yet do it sustainably? And the challenge that we face as computer architects is that we need to do more with less. Now, the first way to do this is we need to understand what the metrics are. How do we think about sustainability? How do we think about water use, carbon emissions, everything else associated with it? So we need metrics and accounting. So in conversations I had with Doug Carneen and others, we kind of see sustainability where power was over 2 decades ago. You need to know how to model this thing. Margaret had one of the first models in power, so that was really helpful. And once you have this accounting, we need to think about how we can design and optimize using the sustainability metrics as yet another metrics with the power, performance, area, and cost. And finally, in order to build a sustainable and develop sustainably, we need to not just think about hardware, but the entire software stack along with it, from programming languages, compilers, and system architecture, and the application spaces also. So that's my challenge to you as researchers, is to think about how we build the next generation of computing systems so that we can actually have a sustainable planet. Thank you.
Hello everyone, I'm Sean Lee. I'm coming from a company called Meta, formerly known as Facebook. So today I'm going to give you some of my viewpoints about research challenges at scale. So first of all, let me show you this frame plots. This plot basically is showing the total computing power by all the computing devices aggregated over different years, so from 2001 to 2025. As you can see from this chart, around 2018, we crossed a line of zeta instructions per second generated by all computer devices in the world. So if this prediction is correct,
And basically, this magnetic model is based on the numbers, the data points across 3 decades. So if this prediction is correct, we are going to see by 2025, the total computing power consumed by all computing devices in the world will cross about 46 zeta instructions per second. So what does this mean? So here I try to explain the trend plots from the perspective of energy. So if we take here 2 bars, I made a couple of assumptions here. The orange bar basically is assuming if your computing efficiency is as good as some of the most modern computer engine like NVIDIA A100 or some of the state-of-the-art ASIC accelerator. So we are talking about 3 TOPS per watts, which is equivalent to roughly 0.3 picojoule per operation. If I use this assumption, you can see around 2015, the total computing energy is consuming around 1 terawatt hours, 1 billion terawatt hours. But if I took a look at the publication, this paper published in 2018, they're saying in 2015, actually, the total computing energy by all devices accumulatively is around 805 terawatt hours, which is about like 800 times of this very ideal assumption made by the orange bar. So let's assume this trend continues. So we are looking at 2025, the total energy is going to be, the total energy consumption is going to be around 100,000 terawatt hours by computing devices. So to give you some contrast, right, the Hoover Dam basically generates roughly about 4 terawatts hour every year. So which means by 2025, to power all these computer devices, we need roughly 26,000 Hoover Dams. That's a huge number. So what are the opportunities at this scale, right? So we are going back to the research topic we have been working on for the last 4 decades, energy efficiency. But this time, it's slightly different because the Moore's law is finally reaching the end. So there are a few things we probably can do. So one thing is like disaggregation. So people have been talking about system level disaggregation to disaggregate CPU, GPU, accelerator, memory, so we can manage these resources more effectively for each task. Another movement is going on is the chip level disaggregation. So you have heard probably in the workshop today on the chiplets, 3D IC, that kind of stuff. And that will also potentially improve your energy efficiency. There are some other things I say from more comments that can actually reduce the power consumption to almost none. So all these are new opportunities we have to think about from devices to the SPL systems. And finally, the holy grail will be how do we achieve a human brain power 25 watts as opposed to a megawatts needed by something like AlphaGo, but it's only good at one test. The other topic that you previously we talked about is privacy and integrity. When the world is more connected, we really care about user privacy and also information protection. So the question would be, what other scalable technology we can actually use to improve the privacy, to guarantee the end-to-end privacy, but also to guarantee the execution to be under a trusted environment. And most importantly, incur very little extra overheads. And finally, the trending topic is what Bobby just mentioned, sustainability. So our group has been working on this for the past few years. There's a paper coming up on Wednesday. They talk about the carbon county to give you a model to estimate the carbon emission during the design time for the manufacturer's environmental footprints. And again, we are talking about design, technology, hardware, software, and we have to optimize all this together to make the system, the ecosystem more sustainable. So here are the challenges, right? As Bobby just mentioned, Japan's paradox. And this is happening by looking at all the emerging applications, including self-driving cars, cryptocurrency, and metaverse. Everything is required computing. And even worse, we are talking about personalized computing. So in convenient truth is we are going to build more data centers to support this kind of computation requirements. And also, we are going to build definitely more chips. And to give you some data points like this, 3 nanometer TSMC fan is going to consume about 7.7 billion kilowatt-hour a year, which is equivalent to roughly 4.5 megatons of CO2. So all these things need to be addressed by the cooperation between government, industry, and academia. Okay, thank you very much.
Does this work? All right, for all the people who are talking, please take your drinks and enjoy them outside. Thank you very much, so that we can hear. I can't hear what's going on even sitting here. So I really appreciate those who are talking. Please enjoy the speech outside so that we can have this panel. Thank you very much. So my name is Bob. I call Stephanie. I'm going to try to talk stand so that everybody sees me. And I want to try to make sure that I also don't fall off this cliff here. There's a very interesting cliff. We're worried that Sean would fall off. So when Samira invited us to this panel, she said that talk about research at scale, but also talk about whatever you want to talk about. So this is my pet peeve. And as you can see, the elephant in the room, besides all the noise, is that is Moore's law. And if we consider Moore's law a 40% increase in density every year, conventional Moore's law, from 2005 to 2015, you get roughly about 30x of density. That's the scale that we're talking about improving. Right? Now, if you go to 1.15x, which is 15% improvement, then you get about 4x out of Moore's law. Now, if you have the same demand as before, which is 30x, then you have to build 7 times more. So without more, we have to build more. And this is a nightmare for our community, not just because of the electricity that we're putting in this, but also because we're going to be building more equipment, and that's going to have emissions from the fabrication. Apple says the emissions from fabrications are around 80% for their cell phones. If we keep our cell phones for a bit longer, we can probably improve that. I don't have the use for a new cell phone every 3 years, so I have a cell phone that's 5 years old. Even if we do that, we're still pushing it down to 50%. The fabrication is roughly around 50% for servers. Again, we can improve that a little bit, but we're just not going to go away, so we have to keep that in mind. The growth trends in AI are, according to a recent MIT technology review, 6x per year between 2012 and 2019. Shin or Bobby, one of them presented 3x per year at Facebook, roughly. So I guess the 2x is coming from extra competition every year, which is also phenomenal. DCs are growing roughly at 20% a year, and IoT is roughly growing at 40%. So there's growth everywhere, and that growth is much, much bigger than what you're getting from Mozilla. Okay, so keep that in mind when you're thinking about research. Okay, so now platform design, we need to minimize the electricity we're putting into our platforms. And there are 3 ways of doing it: integration, specialization, approximation. We've been doing integration. Apple M1 is a great example of integration for laptop. The writing is on the wall for the server, so we'll have a server chip that's also fully integrated. Specialization is with that integration. You also need to identify opportunities where you have to compute or you have to serve a lot, and you optimize or customize your stack for those. And then approximation is not everything has to be perfect. So identify things based on the quality of your outputs, how much you want to do. And you can do this from algorithms to infrastructure. Let's keep that in mind. So that means cross-layer. That means other communities you're going to be working with. And minimize emission fabrication. That's a little bit harder now because we really haven't been thinking about it. But now there's a bit of work thinking about how do we build composable equipment, how do we reuse components, and how do we go to better design. I've also talked in the past about what about all this other novel paradigms that are emerging? Well, CMOS is here to stay for a while at least. So let's think about what we can do with CMOS. And there are a lot of opportunities with CMOS, except that we're emerging from the CPU-centric view of the world, and we have to forego this sort of. Thank you very much. I'm trying to figure out if I can hear the echo of my voice. So I'm going to finish. So Margaret is telling me I'm done. I'm way past my. So, anyways, there's a lot of really good stuff you can do with CMOS and silicon. It's just not going to be CPU-centric. And there are a lot of things we need to rethink. One of the important things that I think we should think about in data centers is that communication fabrics are growing at a faster rate than silicon density, and therefore software is evolving. Okay, metrics and standards. I want to talk about this because this is really important. So, for those of you who can't hear me, can everybody hear me in the back? Yes. Okay, please tell people around you to stop talking. Thank you. So the problem with PUE, which also Artha mentioned, is that when we push to PUEs of 1.1, we're delivering 90% of the electricity to the IT. We absolutely have no metrics for IT efficiency. This is where this community can innovate. This community can fix this problem. We need domain-specific metrics for IT. Online versus batching, we need different metrics, quality control for your output. For applications that have the prediction as an output requires metrics. Representativeness of the workloads. We still see papers in spec, but people are still publishing the spec. How many of you have a paper in ISCA this year that uses spec? Okay, spec is a benchmark suite that was designed for desktops and CPUs and desktops. Okay, so if you're doing that, we're still using PIN to evaluate servers, right? PIN is user level software evaluation. And of course, methodologies and tools. There is a lot of room for improvement there for reproducibility and where we use what tool. This is the last slide I want to present because Sarita asked, what can industry do? Now, how many of you need funding from industry? Okay, that's good to know. So Margaret, you have a really good slide to tell me because we're all coming after NSF. So there's a lot of good opportunity to work with industry on metrics, workloads, and tools because we don't have the right set of metrics and workloads and tools to do research at scale. And this has to be a collaboration with industry, and it has to be a framework where we can also reproduce our results. Post-more means cross-layer. So those of you who are from industry, we need more funding and we need larger scale. We need funding at scale. And I'd like to also use this opportunity as a shameless plug for a recent grant we got from Intel, which funds 5 different groups and 3 different institutions to work on this problem. And it's a cross-layer problem. And we need open collaboration, which means that if we send interns to industry, they should be working on their business.
Okay, so we will actually take audience questions. Our student volunteers, they will place a mic in front, and if you'd like to ask any question, you can come in front and make it clear.
Go ahead and raise it. Okay, thank you. Okay, thank you all. So sitting in the audience over there, I got the impression for some of the young researchers or something here. Imagine I'm a young researcher. Oh my God, all is lost. It's all at scale. You guys are like doing all this stuff at scale. What can I do sitting in a small university trying to come with innovation? What you didn't say is you all are multiplying. You can't figure out that if you multiply something by 0, the answer is 0. You're wasting a lot of energy doing that. you're wasting a lot of energy doing all sorts of useless nonsense. And then you are trying to encourage a lot of academics to worry about your scale problems. So what can someone who is an academic just simply trying to see what can I do over there? Okay, by the way, many years ago, I listened to a talk by Gordon Moore Hardships, where he talked about the growth of the semiconductor industry versus the world economy, and how the semiconductor industry was going to bypass the world economy in a little while. We've all seen things like that before, but help the young academics over here trying to figure out what they can, who don't have access to the scale, especially since a lot of what you all are doing is just useless stuff.
So, Bernie? Was that a question or a comment? Do you want to hear an answer or not? Because we can go either way.
Are we really all doing useless stuff?
So, I mean, I'm proud of what NSF is doing to help a broad set of folks engage. And most of my 5 minutes was on ways that you could get resources out across folks who were not at companies and who were not at the top end institutions. So I'll stand by that. Say that at the microphone.
Yuri agreed with Margaret. Let that
Yuri
be known.
agreed with me.
No, Margaret's the one who's actually funding a lot of the young academics trying to do interesting stuff. Thank you, Margaret.
So again, so thank you, Guri, for the question. I think every panel needs a little bit of provocative discussion, so it's always good to have that. So I think the question you asked again is a valid one, which is if I were in academia without access to the scale that we want to do, how do we do that? And I think the point is not to say that all other research is bad. The point is to say that you want to look at the research that you do with the mindset of thinking about what does scale do to change your problem, right? And so that's what I would do. So I think some of what we try to talk about is how scale changes the nature of the problems that you face. And I think you can apply that to what you do as well. And then Margaret also mentioned a whole bunch of resources that academics have, as well as internships and other research opportunities in the industry that you can look at as well.
Yeah. So, great. I think maybe the room was a little noisy, so we didn't hear what I was saying. I'm saying we should stop doing CPU-centric research. We're done with the CPU. The CPU is going to be sitting in the back, and there's going to be a lot of other interesting stuff that we need to innovate so that we can move to systems at scale. And CPU right now is the bottom. So there's plenty of opportunity for those of you who are young researchers, and many of you who are doing this, and doing research at scale, which has nothing to do with the CPU.
So I think I totally agree with Guri's points. And that is probably one of the reasons I left academia to industry. So basically, I think one of the, of course, like Pastor mentioned a solution for the center students to the industry to collaborate. That's one solution. I think another solution may be the government level need to think about is to build some common infrastructure with industry. So then academia to use this infrastructure supported by an organization like NSF. And hopefully we can work out this together with Google, with all these companies to provide this capability for the academic researchers.
We built it. The size is amazing. Well, we do that. Just copy, well, that's okay. Next question.
Hi everyone, thank you for this really good panel. My name is Abhishek, I'm from Yale, and I had a question about engagement with industry. So, critical part of our community is how to interface with the right representatives from industry, and certain domains like healthcare. I'd love to see a tighter interface between our community and that. What can we do to involve people from, say, Medtronic, Boston Scientific, that community of people in our research work?
Okay, so the question was, how do we engage with the end customer? We talked about all the great problems that computing at scale can solve, and how do we engage with problems like health? I think again, it is a valid problem. So if I look at what Margaret talked about, which was very inspiring to me in terms of looking at the computational photography and the black hole image capturing, I think there are a lot of killer applications that we do engage with. If I look at Kaggle data sets, that's a great example of places where I see a lot of computational systems research using Kaggle data sets to look at stuff. So I think there is a lot of data out there, and there are a lot of killer apps out there. I think it is up to us as a community to engage on the end user problem and focus on that and start working our way back from that.
So I just want to add one thing. When I was graduating from my PhD, the big thing on the forefront was breaking down the DNA, and that work was done with high performance computers from other companies. So I think that there is that engagement, and especially in the medical field, there's a lot of computation that happens now. The question now becomes, how do we make it even tighter and try to integrate that into how we design our systems? And I think in the academic world, you have the opportunity to do that. You are working with people in other fields, and you have this broad disciplinary capabilities in the university. And I would say approach those individuals. I think there's a great opportunity there.
So it was about health, right? So I think I agree also with Bobby that there's a lot of opportunity for AI because it used to be that we're doing simulation and we're doing a lot of HPC, again, CPU centric, but a lot of that is moving to AI. So I think many of us may already be working together with health colleagues. But I want to sort of push this towards what Martha was saying, which is the point I was making was that we need to start looking at cross-layer system design, right? But that means is that we have to work with our colleagues in PL. We have to work with our colleagues in systems, but we also have to go all the way down and work with our colleagues in mechanical and electrical engineering. Right? I think that's really where it's going to be in the future.
So maybe going a little further with that, working with colleagues. I thought it was really interesting to see the discussion of carbon footprint and carbon and life cycle carbon. And I think that one thing I'm wondering for those of you with companies is there enough really incentive for companies to improve that, or is that going to require a policy change? Is that something that we're going to have to work with people who set policy, who work with how to set policy to get enough incentive to actually improve that? I mean, as an academic, it's really interesting. Is that really going to happen?
I think all of us are going to speak up here, but the short answer is at Google, it is a pretty significant priority, and we have publicly stated that in 2030 we are going to go 20% carbon free. And so there is, at least for me, a sense of urgency inside the company to brainstorm how to do that. And every day we face some pretty significant challenges, and there is a lot of incentive to try to help that. Now, in terms of what could be done better, I think the big challenge we face is the lack of a standard vocabulary and metrics. And I know we've talked internally among all the various companies as well to try to see how can we bring public policy to bear so that we have some consistency. And otherwise, what happens is you have different people gaming stuff and honestly incorrect metrics that tend to get optimized.
Yeah, and I completely agree with Martha here that you look at Microsoft, Meta, Google, even Amazon, and every one of them has some kind of carbon goals for the next 5 to 15 years or so. So I think that's coming, and I also, especially through Europe, there's a lot of policy that's coming in to play. So customers that work with customers in Europe, they're asking for their carbon footprint when we work with company X or Y. So those companies are required to provide that now. So it's just a question of accelerating the trend.
So I also have a hat of a nonprofit, which is certifying efficiency and emissions data centers in Switzerland. So I can play the European representative. The regulations are coming in Europe, and Europe has set goals to be have goals, but if we don't have standards and metrics, there is no way that we're going to be able to deliver on this. And I think it would be really a good opportunity for companies to come together and work on standards, because PUE, when you first started talking about it, is 20 years old. And back then we had PUEs of 2, now we have PUEs of 1.1. And guess what? All the electricity is going into the IT, and we have nothing for IT.
So can I add some more points? So I will answer this question, in a different way. So I believe all the software companies, service companies like Google, Meta, Microsoft, we really care about this. If you look at our internal activities, people are very, very have a lot of initiatives to do this. We have like carbon dashboard to measure how much carbon is going to be emitted when you train the AI model, etc. But if you look at the other side, like the design company or manufacturing, they are more reserved. So in that side, I believe you need some regulation or some standardization to push them to publish this number. So I've been talking about like maybe in the future TSMC PDK, they should come with a carbon footprint. So give it to the EDA people, EDA guys can use this information to tell designers how much carbon footprint is generated when you design something like this. So I think that side of the world, they require a lot of the regulation to push them to do that.
Samir is making me answer this question. So Michelle, so NSF, we think about this bi-directionally. I think only one arrow is really going to talk about, which is how to make computing itself more sustainable. But there's the other direction of the arrow, which is how can we, as the globe, use computing resources to understand, adapt, and mitigate climate change. We have huge opportunities there. Commercial entities are going to drive certain accelerator designs and certain system designs, and that's fine. But should we also have science and research attending to where are the accelerators and the scientific problems that will help us do better local and regional climate modeling? We don't have enough of that right now. How are we going to do wildfire modeling? How are we going to do different kinds of hydrology? There's opportunities in that space, and they aren't profit driven, so they aren't happening at the rate we need. And I will say 2 things here. So number 1, we can say you are architects, you should go work on this. I don't think ISCA is particularly friendly to these broad questions when they come in for review. And we need to think as a community, not just the ISCA community, but the ACM and IEEE community, about what it means to publish on these truly broad societal questions. Because if people do the work and can't get it published, we become irrelevant, right? Second thing is about who has access to what data. It's great that all you companies care about this, but there's a huge mind share of people who don't have access to the data they need to move this along with you. And they're in academia. And if you put the data out there, other people will get to work on it too. I'm worried about the brain drain from academia to industry. Item number 3, I love that all my friends are in the question line. I would encourage someone who has never attended ISCA before to get in line and ask some questions. Oh, number 3, awesome, thank you.
I am Surita Ade from the University of Illinois. I feel really bad because I have attended many ISCAs, sorry Margaret. But I want to make one comment and then carry on with that, which is it's just so awesome to come here after 3 years and see nobody's changed. Like Guri's the same, you are the same. It's just cool. But I think for the kinds of things you guys are talking about, we need some fundamental change. And Margaret sort of stole my thunder, but I'll give a different spin to it. I think for these younger people that Guri was so worried about, we should make it really clear that if you're going to do work at this scale, co-design, community, stop doing, little here, little there. It's just doesn't anymore. We have big problems to solve, and let's think about this.
So yes, we could just also add one more point. I think there is a lot of cloud-related opportunities to do things at scale as well. So if, and I give a shout out to Berkeley, for example, which has FireSim, and they do some really compelling at scale work using some cloud resources as well. So that's something for students to think about.
Hi, my name is Edward Hansen from Duke University. So Arthur brought up a good point about the entire reason why the TPU was built in the first place. Is actually to not from a efficiency perspective, but rather from a capability perspective. And I think that is actually something that's more clearly translated to the end user. If they're actually able to do something, then and they can purchase this new technology, and they can see where we can forward progress. However, we see two big talking points so far here. One is capability, and the other part is sustainability. Capability is more clear to you, to the end user, but sustainability is not necessarily intrinsic to when someone purchases a device, for example. So how can we actually translate sustainability towards capability in our devices?
Okay, so I can take a stab at this. So 2 points, right? So I think Margaret mentioned this a little bit. There are a lot of grand challenges in sustainability. Where so to me, when I talk about capability, the question I ask is, can computers allow me to do something that is impossible to do or really painful to do? And some of the challenges that Margaret talked about with climate change, modeling, and so on, are essentially capability problems. So you could think about an accelerator that really increases the capabilities that you have in this space, and that's one way to think about your question. The second option, I think, what you talked about is you said, hey, sustainability doesn't have the same intrinsic motivation that, say, something like capability has because it's not connected to the end customer, and that's fair. But one of the things we do realize a lot of times is sustainability does actually help to the bottom line as well. So the challenge I mentioned in my slide about reducing electricity costs, companies like Google spend like hundreds of millions to billions of dollars per year on electricity costs. So being able to be efficient about that is both green for the planet and green for your wallet as well. So there is some intrinsics there as well.
So I just want to say there's the optimist in me and there's the pessimist in me, right? So the optimist says, if I can tell you what the carbon cost of you doing X on your phone is, that maybe individuals will change their behavior, because if every one of us changes their behavior a little bit, we can then it all adds up, because we're talking 5 billion people, right? The pessimist in me says, at some point, if you're not going to have enough resources, everything is going to get more expensive. And therefore, one way or the other, we're going to have to deal with it. And I'm hoping that we can actually find something in the middle there, because I don't think we're going to get either. I'm hoping we don't get the other end, right?
So, yeah, I think I want to second, a bridge between both art and hobby. So, one of the things that we know is happening is the simulation. A lot of the applications we're looking at complex fluid dynamics, ocean simulation, which is weather forecasts. If you look at drug discovery, which is molecular dynamics, a lot of the simulation applications, they're doing a few iterations of simulation, and then they're building a lot of their go back to machine learning. So when you're looking at a design of an accelerator, you bring those applications in because they're basically various flavors of the machine learning model. So that goes into workflows, right? And that basically, the thing is that when we may have enough money to pay for GPUs, and I know that funding is always a constraint when it comes to research in our communities early. But you can also think about when we run our experiments, if you have a lot of GPUs, think about the cycles you're using those GPUs when you're doing AI models, because what happens with machine learning is that a lot of times you don't really know what to expect from the experiments. We might just inadvertently one experiment because we have the GPU, right? And you worry about the cost of that GPU we give returns to emissions as well.
I will maybe facetiously point out there is one workload where capability and sustainability seems to be at odds, and that's Bitcoin mining. And we can talk about it offline. Thank you so much.
Hi, Timmy from Jordan Tech. So thanks for bringing the challenging and the presentation from the industry of any our skill. So for academia, basically we are lacking of the capitalism and methods to build a system at scale. So we end up building simulators. But as we all know, that simulator cannot equally every single detail that we have from the real hardware. So there is a gap between the simulator and the real hardware system. And we are keeping at the same custom builds. So may I ask whether you can give some suggestions on how to reduce the gap between the simulator and the real system, particularly for the hardware for scale. Thanks.
So I wish I have a beautiful map of all the NSF funded resources that you guys don't use enough of. So one of them is called Chameleon and another is called Cloud Lab. Both of them offer bare metal access to small scale cloud resources, like take small scale data centers, set up at the University of Utah, and I think it's the University of Wisconsin. Bare metal access, so you can experiment on them, changing the operating system. And in fact, some of the recent operating system conferences and SC use that for artifact evaluation across many different proposed ideas. So I think when you say you have to simulate, I would encourage you to step back and say, do I really need to simulate, or do I just need bare metal access? Because there are opportunities there to use these resources.
Thanks for your answer. So follow up this question. I think for the hardware at scale, there might be always floating or open source platform for us to do this. So there might be some imagine or some future application there are lack of such platform infrastructure. So for this kind of thing, we ended up building have to be building a simulator. With all these skills, we ask whether there is any suggestion.
I simulate too sometimes. I'm just encouraging people to stop and think about what are all the evaluation options.
Thanks.
This is Carlos from the University of Wisconsin. So I have a little bit of a naive question, maybe a variant of the opposite of Guri's comment/question. So, I mean, in some sense, academics want to do things that industry is not doing or not capable of doing. It's very hard to motivate a PhD student and say, hey, come on, go do this stuff, go collaborate with industry. I'm like, oh, let them do it, I don't care, right? So my question/comment is, what insights can you share, mostly to industry folks, on the kinds of things you believe you cannot take on as a research project internally? It's actually better done in academia, even though we may have very high error bars because we have simulators, whatever, right? What are those kinds of things that you have, I don't know, past comments, ideas?
Okay, so I'll give you two very specific things that I wish academia would do that I think Google is not pressed to do. Number one, and this goes back to Margaret asking about are there any moonshots that we as a community can take towards as well. I don't know how to simulate Google. So if you could have academia come in and come back with a way of saying like, here is a really nice way to simulate Google, that would be fantastic. And on a related note again, if somebody in academia were to come back and say, if I designed a processor from scratch for a hyperscaler, here's how it would look. I would love that. Because Google will not be able to do that because we have the legacy, we have to kind of think about how we move from things there. Those are really interesting questions that academia can do as well.
Quickly interject, I think you should have just told that to Guri's comment.
Wait, so I thought I did cover. So I think the opportunity within this is to build metrics and workflows that we agree on. And then we look at things they design, which Google is not going to get into anytime soon. And that's why I was pushing on the CPU.
think the answer depends on a lot of factors. So I really think industry, well, depending on who is my boss. So some of the management leadership, they don't believe we should do anything like blue sky research. Very few of them will agree to do that because the stake is too high. They were rather delegated to carry out those kind of high risk, high reward projects. But what is really qualified as high risk is really depends on each leadership or their discretion. So sometimes it's hard. But I would say, most of industry projects, I've seen, industry leadership, their mindset is more like all this research project anyway. At the end of the day, they need to land into the production. So it's not really completely like blue sky what academia is doing. So, but of course, as I said, it really depends on the leadership in some industry, the viewpoints and other research. But I would say most of the companies, even for meta round, try to concentrate our research on the future product instead of giving the blue sky research.
My name is Akshita Sriram. I think my question touches upon what you were asked earlier, which is, so when I'm really wondering whether, staying and collaborating with industry is actually the right approach. And this is coming from someone who did most of her PhD happening in collaboration with Meta's resources and data. And the reason I ask this question is because right now I'm starting to focus on equity and unbiased data center scale computing. And whenever I talk about things like, Partha, when we look at Google's data centers, tons and tons of data centers in the North American region, literally none in the sub-Saharan African region. So perhaps some of these communities are the way they are because they don't have all of these resources. And so when I think about how do we bring the next 1 billion people into the data center computing environment and come up with equitable combinations. And I start having these conversations with industry people. I'm always asked questions about, well, what is the business model? And now I'm spending a lot of time communicating with people in the business school and come up with a business model so that I can convince people in industry to collaborate with me. So what's even the right approach? Because it is kind of blue sky, but this is the kind of research that does need industry access, industry data to be happen.
So I think this goes both to the, in some respects, what you're doing is answering Madhu's point that industry will not be able to solve problems that academia can. So, and I'm sorry to being asked to do business models for academic research. I think academia should not be asked to do such things. I think it's a challenge of the fact that you have to get funding from industry sometimes, which needs to happen. So that's unfortunate. But maybe a different way to phrase your question is, if you'd like to get funding from NSF on this work, what do you need from industry to make that work successful? I would be happy to work with you to make sure that Google can give you whatever we can. For example, Liddy's phrases that help with system design. We've shared with Andrew Chen from University of Chicago, we've shared some of our sustainability data as well. So we're always looking for opportunities to do that, which is consistent with some of our constraints around sharing stuff. But I think when it comes to data, we should be able to have a more easier conversation. I think when it comes to money, there are different funding models that I can see.
Yeah. So, great question. If I look at what's been happening in the past few years, industry, even in North America, they really have a different construction model than they have, for example, in Europe. So in Europe, we don't have the half a gigawatt campuses, but big hyperscalers are building edge data centers, which are in the order of 40 to 100 megawatts. Those data centers are built with utility infrastructure. So if industry at some point has to build in parts of the world because of data protection frameworks or because of proximity to the source, then this would have to be a business model. They have to build it. And there are other reasons why interesting design aspects that come to picture. For example, in parts of the world, not the Sub-Sahara, but if you look at the Middle East, where Dubai is a financial hub, they really have extremely difficult conditions in what they say. So right there, you already have examples of places where people are willing to pay, but the design parameters are quite different from what you can do. So yeah, I think that you know, there are ways in which you can think about the same problem, perhaps in a different setting.
Hello everyone, my name is Andy Mesa and I'm from UC San Diego. My question is related to the availability of, I guess, open source or open source designs that are at the scale that industry is looking for. Specifically, my question, I guess, for Margaret is, are there industry designs that, I don't know, some Harvard Trust or something like that, specifically, I guess, like OpenType and Google, but just designs that are large enough to be representative of the problems that are being faced in the industry, that are actually already available somewhere in the NSF that are being underused. And then for the industry folks, what sort of incentives, I guess, can academia or some other place offer in order to make some sort of benchmark openly available for researchers to use? I understand we can go to industry and do internships, but when we want to share this benchmark with somebody, that's often a very difficult time, or one of the major challenges. And I think a really great example that at least has benefited me is the OpenType and Google.
So NSF doesn't have any research internally, so it's not like we have some stash of open source designs we're sitting on. We do, however, I will just say we have a new program, Pathways to Enable Open Source Ecosystems, which is about helping people scale out from having an open source thing, could be hardware, could be software, to building out a community around that open source thing. So I hope that would incentivize a few more contributors to stand out on open source hardware. There was also a workshop a couple days ago, I guess it was only yesterday, about open source systems as well. So I think this drive has actually helped because many of the processors are open source, and so that's helped some of the information sharing. That's what I can do from the NSF perspective.
The other resource I would offer is the Open Compute Foundation. They have a whole bunch of reference designs. It's a little bit at the server firmware BIOS level, but there's a lot of architectural resources there as well. The chip challenge is the other place where there's a lot of commercial grade open source instantiations you might find in some stuff.
Margaret wanted a question from someone from outside the community. This is my first ISCA'22 roommate for full disclosure. I'm totally confused by this app. All I heard was in the post-war era, the world is ending. All of you presented a ton of problems, and then alluded to solutions coming in from outside this community, from the key guys, or the system guys, and the algorithms guys. But no new brilliant architecture idea. So my first ISCA is also, this is also my last ISCA. Are you guys out of ideas that should not get just fund systems researchers and algorithmic researchers? Because we can take a lot of the problems, for example, with deep learning, and say, so producing a trillion parameter model. I can produce the model with 2 orders of magnitude fewer parameters with very low accuracy. That's what the algorithm is doing. Should all the funding and effort go there? Our architects out of ideas.
I have to apologize to Jignesh because is my classmate from housemate from Wisconsin and from the database community. This is a really good question. I think we should all listen to, especially those younger members of the community. What we need to do is cross-layer design. Without architecture, you're not going to have a platform. The ideas can also come from the architecture because architects know what's happening at the lowest level. If you look at pushing efficiency without more, there is a brand new way. The brand new way is you won't have a CPU as a database person. There's not going to be a CPU. Now you can think about how do you implement what you want to implement in your database services with co-design, which is what Arthur already talked about, together between algorithm, software, tool chains, all the way down to silicon, and eventually also infrastructure. Because that's what we're doing. If you see that, that's what we do with smartphones, now we're doing with laptops. It's going to be a complete cross-rails. I hope I answered that question.
I think I will point out that the past 5 years, we've had some of the most amazing architectural advances that at least I have seen in my 3 decades of research here. Things like the TPU, the VCU, these are phenomenal accelerators that give a run for the money for the early Eckert-Mobley machines and so on. So we are kind of at a very interesting stage. So this is not to say that architecture research is dead and we are not doing any new ideas. This is to point out that the new ideas are all being brought in with a deep appreciation of the stack. And this goes back to the early 60s or even earlier. When you look at the very first computers, they were all cross-layers. And so they were fantastic architectural contributions, but they were cross-layer. And for a while, we went into more narrower architectural contributions where we said, hey, look, I'm going to increase my pipeline depth and I'm going to do auto-product execution and value prediction and speculative design migration. And none of you guys knew about it. And now we are going back to the past where we are saying our architecture, we are going to build an amazing kick-ass database accelerator, but it will be working with you. So it's not that architects are not going to be designing anything new. We're just saying that all the new things are going to be amazing because we're going to do it in collaboration.
Amen. Hello.
My question for you guys is, I understand that the age of CPU is coming to an end. But the question is, the successor is still not ready for all applications. Now, to what extent do we still invest our resources into CPU data? The CPU is ready to continue to serve our needs at least 5 to 10 years.
Sorry, I was talking about coordinating on your question. Your question was about CPU.
Yes, my question is, the age of CPU is coming to an end. I think we all agree with that. For the next 5 to 10 years, we will have a replacement for many applications. So to what extent do we still need to invest in those research to keep our current demands in the short run?
So when I say we need to rethink platform design for the CPU, I don't mean that we're going to get rid of the CPU. I think the CPU as we know it and the operating system as we know it are going to be taken backstage to all of these other co-design functionality that's coming. And the CPU and the OS basically need to be the control plane to set up access to resources, partition resources, and give hardware access to all of the accelerators and the other functional blocks we have to do the work without getting the CPU and the OS in the line. So if you look at it, the basic organization of today's server, it's a desktop of the 90s. If you look at the sockets, you look at the memory, the way it's connected, the hardware speed, the network is I/O, but the Linux operating system, which treats the network as I/O, right? But what everybody wants to do in a data center is get to the data while the CPU is holding the data hostage. So we need to read this is where I think academia comes in, because we're both not going to dive into this tomorrow. Academia, they think about a new lane of the future where this vision is implemented from scratch. It's like with the CPU, the OS, and all the accelerators there, so that it can bring efficiency to automation.
I agree with you that the CPU is a very good load control system, but you don't invest in research to make it more power efficient, more area efficient. I higher latency, they were holding back these accelerators, and now say your accuracy and high considerations with payment associated processors and
if most of the work is done by the accelerators, and I think we might be okay with the existing research in CPU. I'm not saying we should stop doing research on CPUs, but I think that we should go beyond CPUs for the next generation. Last question, everyone. Last question.
Thanks for the attention. I'd like to first thank Margaret for explaining this resources. I'm Karthik here from Yale University. I work with Untitled Chapter. My question is, what are your thoughts on designing longer lasting devices that are modular and replaceable, like a desktop PC? What technologies and research do you think is needed to enable this? For example, there have been concept phones like CodeBlocks or Project Ara by Google that start off by keeping modularity in mind, but all of these seem to drop off in the end. Project Ara like now doesn't include modular conflict. So do you think these haven't materialized for smaller devices like smartphones because there's some kind of tension against performance, or do you think there's other reasons, or do you think it's just recently that sustainability has become a priority for various reasons? Thank you.
So there are requirements coming out of Europe, like right to repair, for instance, that where you want to keep the cell phones around longer, you want to enable people to be able to use their cell phones longer. That also is not just a hardware issue, it's a software issue too. We throw away our cell phones because we run out of memory or we run out of storage or whatever it might be, but not because it actually doesn't work. So I think there's a lot of questions coming in that way that we think it, and I would actually challenge people, can we keep our cell phones running for 20 years? I would love that. Can we keep our processors going for 20 years? Can we make a server that lasts for 20 years? And does it even make sense? I mean, think about what innovations are coming up. I would love to see that kind of research and what that means.
So that's interesting that you brought it. I think what the concept phones that I was talking about, like CodeBlocks and Project Ara, what they were about is having an interface and then upgrading the individual components, but they can still communicate with each other using the same interface.
So I think since you asked about Project Ara, so the insights from that are being used in the Pixel phone. So the one thing you have to think about is when you talk about sustainability, there are three kinds of stuff: scope 1, scope 2, and scope 3. And sometimes it actually makes sense to replace a part because you get to a more higher efficiency part. So it's not as simple as just keeping a part forever. But I think, like Bobby mentioned, there are regulations coming in, and on the server side, there's a whole bunch of modularity in play that I think you'll be very happy with. Okay, thank you for the question.
And thank you for my last question.
Thank you, Samir. I think this was the first time I've seen a panel at the reception. It was a very brave thing to do, and a quick round of applause for them.